welcome everybody to the third season of the One Word of Nature seminar. So it is a great pleasure to meet you all in the Zoom room. And of course, we very much enjoyed this seminar in the last year. Hopefully this is the last season, which also means that after, let's say, 2-3 months of online talks, we will be able to go back to what we call normality, to meetings in person. I already received some invitations. Yeah, it's very difficult to say yes. I will attend, for instance, the next SIAP meeting or other meetings in Poland or in Portugal in summer. But this is our big hope, that at the end of the third season of the OWOS seminar, we will be able to attend meetings in person and conferences. And this is my greatest pleasure to have as an opening speaker of this third season, Hedy Attouch from Montpellier, who is well known for his outstanding contributions to optimization, but in particular, also to the fact that he was able to emphasize the connections of optimization to other mathematical fields, like dynamical systems, mechanics, partial differential equations. So Hedy Attouch is one of the greatest mathematicians we have in our area. He had tremendous contributions, and I would like to mention only the great work he did in the last 1-2 decades on continuous and discrete time approaches for optimization, on the development of fast algorithm for convex and non-convex problems. So it is a great pleasure to have you as opening speaker of the third season. So the talk today will be on acceleration of first-order algorithms. The floor is yours.
Okay, so thank you, Radu, for this kind introduction. Thanks to the organizer for this great seminar. And I'm going to report on recent progress concerning the acceleration of first-order algorithms, mostly based on the joint work with Zaki Jbani and Riyai from Morocco, from the University of Marrakesh, and Jalal Fadili, who is in France, in Caen, and from the EUF, a prestigious institute. Right. So the setting of the lecture is the following. Well, we are going to be mostly interested with convex optimization. At the end of the lecture, we shall consider more general situation like monotone inclusion, but for the moment, most part of the lecture is devoted to convex optimization in a general real-world space, since we are interested both in application in finite dimensional spaces and infinite dimensional spaces. The state of the system is denoted by X. Here is the dot product in the real-world space, and here is the norm. And we're interested in minimizing a function f from H into R, which is convex differentiable, mostly using its gradient, and we assume that the solution set is non-empty, and we want to solve by fast first-order method this minimization problem. And the tool we are going to use may be sophisticated. You see, the problem is very simple, but the tool may look at first glance quite sophisticated. But in fact, we are going to see that it gives rise to rather simple algorithms. And this equation, you see here, is x of t, the state of a system at time t. X dot is the mechanical notation for the velocity, it's the velocity vector, and x dot dot is the acceleration. And here is the basic equation from mechanics, the Newton equation from mechanics. From one end, you have m times the acceleration. Here, the mass has been normalized equal to 1. And here, you can imagine on the right-hand side, here is the force which is exerted on the system. Here is the conservative force, which derives from the potential f or the objective function f in optimization. D of t is just a temporal scaling factor. So if you have only this term, you have a conservative system which exhibits periodic or quasi-periodic trajectory. The optimization aspect comes from the damping force, see, which dissipates the energy and makes the system stabilize to a minimizer asymptotically. And the damping force is the sum of two terms with specific properties. One is a classical viscous damping, that is to say the matrix, the operator which acts on the velocity is just the identity, with a particular situation that the coefficient, what we call the viscous damping coefficient, goes to zero as t goes to infinity. And in a very special way, like alpha over t, we shall see what conditions are of alpha. And it's very important to have this precise rate of decay of the damping at infinity in order to enforce a rapid method. In fact, rapid method like Nesterov method. In fact, it's important, if you have a damping friction which is too big, then the inertia is killed and the system just behaves like a steepest descent method and you have just 1 over t. So it's important in order to enforce the inertia aspect to have a damping coefficient which, let's say, asymptotically is small. But if you just do that, let's say Nesterov method, then you exhibit oscillations. And oscillations are not good from an optimization point of view. And that was the main criticism that people did concerning inertial method. They say, oh, inertial method, okay, well, fine, but I don't want oscillations. And these terms, we are going to see that it mostly kills the oscillation. It's now the operator, you see, takes care of a geometry of a function around x of t via the Hessian of f at x of t, right? So these two damping terms have specific property. This one is related to accelerated gradient of Nesterov, and this one, governed by the Hessian, neutralizes oscillation. But you may say, okay, the Hessian is a nice mathematical object, but when doing numerics, I don't want to work with the Hessian. In fact, we are going to see, just like a paradox, that this dynamics with the Hessian term is even simpler than without the Hessian term. This looks like a paradox. I'm going to give you at least 2 or 3 explanations of that. The first explanation is that the Hessian doesn't come into the dynamic alone. It acts via, it enters via the action on the velocity. It's the action of the Hessian of f at x of t on x dot, which comes into the dynamic, right? And this term is nothing but the derivative of the gradient of f at x of t. That's the fundamental. If you want to remember something from this lecture, just remember that. That's the key idea. It's a very simple idea. This term is the derivative of this one, which means that when you discretize these dynamics, what appears is just the difference of a gradient at 2 consecutive terms. And this is free. You see, it's completely free. You just have to keep memory of a gradient of f at the preceding step. And this is exactly the structure of an Nesterov algorithm. You have just this, what we call correcting term, which has a tremendous effect on the behavior of the dynamics and the algorithm. And the result you obtain for f convex with a gradient which is L Lipschitz continuous and alpha greater or equal than 3 and SL less than 1, classical S is the square of a temporal scaling factor. Then you have the optimal rate of convergence. You know that with gradient methods, you cannot do better than that. So you get it. And moreover, you have fast convergence of a gradient to 0. This is a very good estimate, you see. This means that the gradient actually goes fast to 0. And moreover, there is numerical evidence that the algorithm behaves very well and the oscillations are killed. So the lecture is organized as follows. First, we are going to survey for people who are not familiar with the subject, I'm going first to survey rapidly the state of the art concerning inertial method in optimization. Then we are concerning the introduction of the Hessian, first in the continuous dynamical case, then in the algorithms. Then I shall describe numerical experiments, which are mostly devoted to lasso type problem. Then we shall describe some recent results concerning related systems. Then we shall enlarge the topic to the case of monotone inclusion. And if we have time, we can talk about perspective and give many open questions to consider. So let's start with a survey, rapid survey. Let's start with the so-called now well-known heavy ball with friction method of Polyak. So it's a whole method first introduced in 1964, which is here. It's a very simple dynamic, and the damping here is a fixed positive damping coefficient. So it's an autonomous dynamical system. And if you want to have a mechanical intuition of this dynamic, think to the following picture. Here is the graph of F, the function you want to minimize. It's in product space H cross R, right? And imagine that you have a heavy ball. Here the mass has been normalized equal to 1, a heavy ball, which moves on this surface under the action of three forces: the gravity force, the reaction force, which is normal to the surface, because M is subjected to stay on the surface, and the friction force, which is opposite to the velocity. Okay, and mechanical intuition is that the trajectory M is going to finally end with local minima, depending on the inertial on the initial velocity and position. You may imagine that you cannot end up with this point or this one. So it's a wonderful tool if you want to explore local minima. But in this lecture, we are considering convex optimization, right? So we are going just to use this dynamic as a tool to accelerate the algorithm. Classical result concerning the PV ball method. In the general convex case, that's a disappointing point, you see, is that you have no, because the friction is too big, you see, too much friction. So this term is negligible with respect to the velocity. So you can forget in some sense about the acceleration, just the same speed as the steepest descent method. And in Alvarez paper, the second paper of 2000, it proved that the trajectory converged weakly to an equilibrium. In the strongly convex case, that's a very interesting case of heavy ball with method. In the strongly convex case, if you choose the damping coefficient accordingly to the geometric property of a function, if a function is mu strongly convex, then you take a damping of this form. You can take over damping, but this is the optimal one. Okay, if you take this viscous damping, then you have exponential convergence of a trajectory. So in this result, we already see that in order to have fast method, there is a connection to find between the geometrical property of a function and the choice of a damping coefficient. Autonomous system, there is again a new interest about the dissipative autonomous system, and there are many interesting things and new ideas which are developing in this setting. You can consult the Springer book, briefed by Arogen Duby, and also with Bott and Chesnek. We published a paper recently in Journal of the European Math Society with many new direction of research concerning dissipative system. But at this moment, we are not able, with autonomous system, we are not able to obtain optimal rate that is 1 over t square or 1 over k square with autonomous system. This is a big open question, so that's why we move to non-autonomous system. From now on, we're mostly considering the case where the damping coefficient depends on t. Right, if gamma of t is bounded away from 0, then you are more or less in the case of heavy ball method of Polyak. So the interesting case is when gamma of t goes to 0 as t goes to infinity. That's what we call asymptotic vanishing damping, which means that asymptotically, when t goes to infinity, this coefficient goes to 0. Of course, it's not allowed to go too rapidly to 0, because if it goes too rapidly to 0, it's just like if you have 0 here. So you have a conservative system, no optimization property. So allowed to go to 0, but not too rapidly, and this you can measure it with this integral. This integral, if you want to keep the optimization property, this integral has to be plus infinity, plus infinite. This means that the critical case for gamma of t is 1 over t, or constant over t. That's the smallest damping coefficient you are allowed to take in order to get optimization property. And we are going to see, just like always, critical situations are often the most interesting to consider, which we're going to see that's precisely the case of an Nesterov acceleration method. Recently, with Alexandre Cabot in Journal of Differential Equation, we have performed a general analysis of this, the asymptotic behavior of the system in the case of a general gamma of t. So we introduce this function, which depends on gamma, and under this very simple condition, you see the product of gamma of t times capital gamma of t, which is defined like this. If it's less than 3 over 2, then you obtain this rate of convergence. So it allows you to cover all situations you can imagine. And if you return to the critical case, gamma of t equal alpha over t, we're going to see that the coefficient here is going to play a fundamental role, which was not obvious from the beginning, just from this theorem, okay? Then elementary computation gives you that gamma, capital gamma of t is t over alpha minus 1. So if you compute the product, you see, t cancel, you get alpha over alpha minus 1. And alpha over alpha minus 1 is equal to 3 over 2, precisely when alpha is equal to 3. So by this way, you find the critical situation of Nesterov. And this makes a natural transition with this dynamic, which was put to the fore recently by Suboid and Candes as a continuous dynamical interpretation of a Nesterov accelerated method. So from the preceding, you see that when you consider damping of this form, the critical situation is alpha equal 3. And surprisingly, historically, Nesterov did consider the critical case. It's the critical case that he considered, the case alpha equal 3, or more or less equivalent to alpha. It's not exactly this, this expression, but it's equivalent, okay? For alpha equal 3, you get this result. But most interesting, if you take alpha greater than 3, you get better result. You get, instead of capital O, you get small o, and most important, you get convergence of the trajectories. That's specific to the case alpha equal 3. For alpha equal 3, it's an open question to know if the trajectory do converge. If you just replace 3 by 3.1, then you have mathematical guarantee of a convergence of a trajectory, even in infinite dimensional space. And for curiosity, the subcritical case has been examined recently by Apidopoulos and Joel Sal. And you have the following picture. Sorry, you have the following picture concerning the convergence rate. Here is the graph of the exponent, 1 over t at some power is the graph of the exponent in this formula. You see that the exponent grows linearly from 0 to 2 when alpha goes from 0 to 3, and then it's stationary. And these rates are optimal, that is to say they can be approached arbitrarily closed. For alpha greater than 3, the optimality is obtained by taking a function which becomes very flat around its minimum. And for alpha strictly less than 3, the optimality is obtained by a sharp function, just the opposite situation. Now, when you come to the algorithm, if you discretize this dynamical system, it's classical discretization, there is some flexibility. The sensitive point is at which point do you consider here, okay? You have many different choices. You take xk minus 1, xk plus 1, so convex combination of them. okay, there is a lot of possibility. If you take yk equal xk, then you get the Hedy friction method. If you take yk equal xk plus 1, you obtain the inertial proximal algorithm from Güler-Beck-de-Boule, which is a particular case of Vista method. And if you take yk equal to this quantity, you get the Nesterov algorithm. So again, why Nesterov? Why this choice of yk? And again, at this stage, there is a very natural explanation for that. Because when you pass from the continuous dynamic to algorithm, a universal way to preserve the convergence property, the asymptotic convergence property, is to do implicit discretization. There are many deep theorems in mathematics and physics, which are based on Trotter, Kato, Lie formula, and so on, which tells you that the implicit, that exponential formula, the implicit discretization, does preserve the property of the continuous dynamic. So when you consider the inertial proximal algorithm, you are confident that you are going to preserve the convergence property of the continuous dynamic. So, but you are not too happy with proximal algorithms. They are good, but may be expensive to compute. So the idea is just replace the prox by a gradient step. Instead of taking a prox step, you just take a gradient step and you have Nesterov algorithm. So Nesterov algorithm is just the inertial proximal algorithm where you replace the prox by gradient steps. And that's the reason why implicit and explicit algorithms, they do fit very well. Okay, here is the picture of a Nesterov algorithm. Here is the extrapolation step, and then you take a gradient step. Here's the prox, quite the same structure, extrapolation step, and then you take a prox step. Okay, the optimality is at the end. Okay, here the optimality is at the start. So here it's implicit. And in fact, the two, because of a reason I gave before, the two of them, they fit very well one with the other. You see, when you consider the proximal gradient algorithm, which now associated with minimization of f plus g, where g is non-smooth and f is smooth. Okay, here is, let's say, the Vista method. You have exactly the same kind of result, you see. All the case, you have exactly the same kind of result. And you have exactly the same picture. And okay, it's a very nice algorithm. Okay, and congratulations to Beck and de-Boule for introduce a very nice system. But usually they don't like to call it Vista, since Vista is not exactly this expression, but it's an equivalent expression, you see. Okay, but they do have the same asymptotic behavior. Now let's come to the main part of our lecture, which is the introduction of Hessian. I first introduce it from a dynamical point of view, and there is a rich history, you see, just like important notion, you see, there is a big history behind it. Maybe the first paper which really considered this question was a paper, the seminal paper by Alvarez in Psychon 2000. You can read it now. It's still a very actual paper, very nice paper. And he already had the intuition that it's important to adjust the damping matrix. Here now it's a matrix, you see. It may be anisotropic to adapt the matrix, damping matrix, to the geometry of F. But he was able to do it only in special situations. For example, when F was a quadratic, convex quadratic, positively definite matrix, function, sorry, then he was able to do that and see how to adapt gamma. It's only a couple of years later than with the help of Jérôme Bolt and Patrick Redon that we extended the idea of Felipe Alvarez by introducing, instead of a gamma fixed, we introduced a matrix which takes account of a local geometry of the function, which is Hessian. But still, you see, at that time, we only knew Nesterov, the Hedy method, so we worked with a fixed damping coefficient. Okay, but already this dynamic was very interesting, but we didn't have fast convergence result. It's only recently, you see, 2016, that we took advantage of a recent progress of Suboil and Candes by considering the case of asymptotic vanishing damping. We take alpha of t instead of gamma. We pass from the EV ball to the Nesterov method, right? And at that time, we are only able to analyze the behavior of a continuous dynamic. We are not able to pass from the continuous dynamic from the discrete algorithm. It's only very recently in the paper in which I'm going to report with Shbani, Fandili, and Riyai, that we have been able to develop an algorithmic analysis parallel to the continuous case. And I'm going to explain what, you see, passing from the continuous to the discrete was not so easy. And there is a lot of interest in recent years concerning this kind of system. There are many works from Jordan and his many students in California. Castera, Bolt, Favored Powers have been considering application to deep learning. Bolt, Chesnek, Laszlo have been considering this kind of dynamic with Tikhonov rigorization term, which is important too. Well, at the end of the I'm going to report at the end of the lecture on recent development by Aleska, Laszlo, and Pinta, and by Samir Adli and I concerning this system. Right. So here is in the continuous case, it's a numerical experiment. Just to give you some intuition, we took a function voluntarily, which is ill-conditioned. You see, you have two eigenvalues which are very different one from the other. It's very ill-conditioned. Okay, and in blue is, let's say, the continuous dynamic associated to Nesterov, asymptotic vanishing damping, you see. And in blue, you see that there is, because of this ill-conditioned aspect, you have a very narrow, deep valley, and you have many lateral oscillations, and you have this curve in blue, which is awful from optimization point of view. It converges, you're right, but with many oscillations which are not desirable from the optimization point of view. Here is the value, and here is the trajectory, the same thing, you see. And if you introduce just beta equal 1, that is deviation damping, then now you forget completely about this oscillation. You see, it's a tremendous effective tool. Right, so we want now to make this more formal from a mathematical point of view. I just want to add one word, because I've been insisting on the introduction of this system from the point of view of the damping of oscillation system. You can introduce this dynamic from different point of view, which is also very interesting, is the connection with the Newton method, not Newton method from mechanics, but the Newton method for solving equations. You see, Newton is some universal guy. He done two fundamental things concerning mechanics and concerning solving equations. Now it's a Newton method for solving equation. He's the same guy. So F is convex. You want to solve this equation by the Newton method. So you're in xk, and you linearize the equation at xk. So this gives you xk plus 1. And you can see this equation as a discrete version of this continuous dynamic, right? Since this term, up to some normalization, you see, it's just the discretization of the velocity. So it's deviation acting on the velocity plus a gradient of that. So it's a very simple equation. The problem is that it's ill-posed. If you want to do mathematics, the only thing you can say is that this term is derivative of this one, so you have first integral, and then you stop. You cannot say anything more. That's a pity, you see, it's ill-posed. When you have an ill-posed problem, there is a universal way to overcome the difficulty is to regularize it. You know, for example, Tikhonov regularization, but here you regularize it with respect to the velocity, not respect to x, okay? Because the degeneracy comes from this matrix. This matrix may be degenerate, okay? So you add some constant time the identity in order to get a matrix which is no more generate. So gamma of t is a regularization parameter. It's called the Levenberg-Markov regularization parameter. And now this is a well-posed equation. We have been studying this kind of equation with Benner-Zweiter in SciCon 2011, and we have been studying this equation in much more general situation with general maximal monotone operator. And we have seen that this equation is well posed with very weak condition of gamma of t. Gamma of t is not to be too small. Too small in the critical case is exponential minus t. So you really need a very minimal assumption gamma of t in order to have a well-posed equation. So that's a system which is very nice. And you see that the system we consider, it just comes just by the introduction of the inertia in this system. Okay, that's what we call it dynamical inertial Newton method. Newton method, regularized Newton method, and you introduce an inertial term, right? And ultimately, what we do is to take gamma of t of the form alpha over t in order to get connection with Nesterov. So that's another way to introduce our dynamic. So now I have to go rather rapidly across the mathematical analysis, which is quite standard. It has been done, as I said, in the continuous case in the Journal of Differential Equation 2016 with Pepouquet and Redon. And it's just based on the Lyapunov analysis. So you have a convergence rate 1 over t squared, you estimate on the gradient when beta is strictly positive. And just the point is to introduce the right Lyapunov function, right? The Lyapunov function is quite natural. You see, if you develop this term, you just end with a composition of the global mechanical energy of a system, potential plus kinetic, plus some anchor function, which is the norm of distance, the norm of x of t minus x star when x star is in equilibrium, right? And it's important here to have a coefficient, you see, of order t squared. So the ultimate point is to get that this function is decreasing, so bounded from above. It's bounded from above. This term is non-negative. This means that this is bounded from above. This is bounded from above. This gives you the rate of convergence 1 over t squared. And so that's the proof, you see. Since you know the shape of a Lyapunov function, you derivate it. You use the constitutive equation and some convex inequality. And then you end up with, you see, alpha greater than 3 just appears here in order this term to be non-negative for t large enough, right? And beta strictly positive enters here in order to give you that this interval is finite. So the proof in the continuous case is there is nothing exceptional. For alpha strictly than 3, as I said, you get additional estimates which allow you to obtain convergence of the trajectories. This dynamic is very stable. You can introduce external perturbation. You just need them to go to 0 sufficiently fast in order to preserve the convergence. In the strongly convex case, in fact, it's more interesting to return to Polyak EV ball, you see. You may work with the Nesterov coefficient, alpha over t here, but if you do that, you have less good result. You have very good result, but less good that with a fixed, see, the EV ball is very good for strongly convex function. For strongly convex function, it's more interesting to take an autonomous system like this. So you take exactly the damping, which is adapted to the mu strongly convex coefficient of f. And in that case, you have exponential convergence of a value and exponential convergence of a gradient to 0. Right. So let's come to the gradient system. I don't know how much time I have to.
I would say 15 minutes.
15 minutes. Okay. So okay, I don't waste time. Let's talk now about the main part of the lecture, which is concerning the algorithm. And I said it's a result which had been recently obtained with Bani, Fadili, and Riai. And when I refer to this paper, I call it ACFR for short. So if it's convex, the gradient is L Lipschitz continuous. Here is the dynamic. Here is just some rescaling. You see, this term is negligible, but it helps to simplify the computation. Okay, but you may forget about this term if you want. You discretize this system. As I explained at the beginning, here is appearing the difference of a gradient at 2 consecutive steps. And here you have a choice for yk, and you do the same choice as for the Nesterov method. Okay, and you end up with this algorithm. Right, and here's the classical structure of the Nesterov algorithm, but you have additionally this correcting term. Recently, there has been a related algorithm introduced in a different way by Shidu, Jordan, and Su. You can find it in archive, right? And Lyapunov analysis, you see, the idea is to follow the same proof as in the continuous case. But indeed, it's much more easier to do that in the continuous case than in the discrete case. Why? Because in the continuous case, you have the power of differential calculus, integral calculus, and Grandval-Lehmann. You have a lot of tools, you see. In the discrete case, you see, life is much more complicated. Okay, fortunately, you can be optimist, since you can say, okay, we succeeded in the continuous case, so we have to succeed too in the discrete case. You see, it gives you a structure of a proof, but not the proof. So here is the result, which is quite similar as in the continuous case. You see, rate 1 over k squared, fast convergence of a gradient, and for alpha strictly greater than 3 convergence of the trajectories. But in the proof, there are some technical aspects, and one of the main aspects is that we have to use a reinforced version of a gradient-lessoned lemma. Right, and which is specific to the convex case. You see, here is the classical gradient descent lemma. In the convex case, you have this additional term here. And this term will play a fundamental role in the estimate. It helps to get quantity less or equal to 0. Otherwise, if you have not this term, you see, you are stuck. And so this is one of the reasons why it took so many time, you see, to go through this proof. There is also the fact that we introduce this correcting term here, you see, which also helps to make the proof simpler. Otherwise, it's even more complicated. So finally, we succeeded and get the result. In the strongly convex case, we rely on the, let's say, heavy-wall type with Hessian dynamic, and you end up with exponential convergence rate. No surprise. In the non-smooth convex case, the idea is to replace F by its Moreau envelope. So that's a very general and very efficient idea when you have to work with a function f, which is not smooth. The classical idea is to approximate f by its Moreau envelope, okay? That's a very good tool. But another idea is not to approximate, but to replace. This makes a big difference. That is to say, you argue with a fixed proximal parameter. Lambda is not intended to go to 0, because if lambda goes to 0, at the limit you have a non-smoothness. You have to face the non-smoothness. So you don't want to face the non-smoothness because you have an inertial dynamic with non-smooth objects which are going to exhibit shocks, and so you don't want that. Okay, so you fix the parameter. So you not approximate f, but replace f. This is a fundamental difference. And if you do that, then you can take advantage of a classical proximal calculus. Now, classical with the work of Bausch and Company. You can find all the results you want in this wonderful book. If f is strongly convex and f lambda is strongly convex, you can have a formula for the gradient of f lambda, for the prox, and so on. So just what you do, you replace f by its Moreau envelope, and you obtain this algorithm, and you obtain similar type of convergence. The main difference is that now you have no more of a gradient of f, but only the prox which appears. You see, there are 2 different prox which appear in the algorithm. If you are able to compute the prox, then you can develop the theory. let's go to a numerical experiment. We have been experimented the method on the lasso type problem. So you regularize the least square problem, a classical one. G is a regularization term, just like L1 norm. And so we cannot apply directly our method to F because F is non-smooth. If I want to regularize, so I cannot compute the gradient, or I have to go through subgradient method. If I want to compute the prox, I'm not able to compute the prox, since the prox is as difficult as the initial problem. And so we are going to use a trick, a very nice trick, which consists working with a different norm. And this is specific to this kind of problem for regularized least square problem. So you introduce this matrix, which is defined here. A star is the adjoint of A. If lambda is small enough, then this matrix is symmetric positive definite. So the idea is to apply our algorithm, the gradient algorithm deviation, not to F, but to Fm, which is the Moreau envelope of F in the matrix F. So the Moreau envelope of F is convex, its gradient is Lipschitz continuous, so you're allowed to do that. Here it's defined, you see, it's the Moreau envelope with respect to the metric M, and the trick, the wonderful fact is that the gradient of F with respect to the metric M is precisely the operator you are interested with. It's the classical proximal gradient algorithm for this kind of problem. Okay? It's a gradient, but it's a gradient with respect to a modified function in a modified metric. So if you do that, you have a completely splitted algorithm. Okay, the prox of a non-smooth function G, for example, the norm 1 appears here, just soft thresholding truncature operator. So you have the algorithm, you apply it, then you have the convergence rate as we claimed at the beginning. And here is the picture. It's a wonderful picture. When we discovered the picture, we were very excited since we compared. Here is blue is the algorithm deviation, in red is phi star, and in black is the predicted rate 1 over k squared. Okay, and you see that the introduction of deviation has fantastic effect. You see here we have 10 power 10 minus 10, 10 minus 15. So it's tremendous, you see, convergence. You may even conjecture that there is some kind of linear convergence here. So we tested it on the L1 problem, lasso problem, then L1, L2, same picture, TV problem, nuclear norm, always the same time. Right. So if a few minutes, I want to talk about 2 or 3 of the systems which are related to this one. First one is something we discovered very early, is that this dynamical system is equivalent to a first-order system, which involves only first-order derivative in space and in time. Okay? And it's not the Hamiltonian formulation of a problem, since if you take the Hamiltonian formulation, you still have deviation. The idea is that in this equation, each terms appear with its derivative. This term is the derivative of this one. This term, sorry, is the derivative of this one. So in some sense, you can integrate this equation. And now the equation you have here just appears in the product space, you see, as a perturbation of a gradient step, gradient 0. And here is a perturbation, it's a non-autonomous linear perturbation of a gradient system. So what's very exciting is that now this system makes sense for F non-smooth, F non-convex. You can consider constrained shocks in mechanics, numerical application, but what has been done by Castral. So this formulation opens a gate to a very large field of application, since this makes sense for, under very weak assumption, you can do Kurnikal-Loyazevich, but we fixed parameters. And I must say that what's not nice about this is that when we work with the system, you lose the mechanical intuition. You have no more intuition about the system. What's the system? You see, the way these coefficients are related one to the other is rather integrated. You see, you have no more intuition. And when we discovered this in 2002, we tried to discretize this system in order to get a nice result for algorithm, but we failed. We are not able to do that, you see. We wanted to have better than Nesterov, but we are not able. You see, the fast convergence of a gradient, we are not able to prove it in this system. It's complicated. Apparently, Manger and Labarre recently have been able, but it's not still published, so it has to be confirmed. They have been able to discretize the system to obtain fast convergence result. Another interesting result, dynamical system related to this, is what I call implicit Hessian method. Okay, here it's a first order method. The gradient here, there's no more Hessian, but the gradient is computed not at x of t, but x of t plus some coefficient time x dot. And what happens is that as t goes to infinity, x dot goes to 0. So if you do the Taylor expansion of this term when t is large, you obtain this. Okay, so you make appear the Hessian you see as the next term in the Taylor expansion. So asymptotically, this system behaves just like this. That's what we call it the implicit Hessian. And what's nice about this system, it's the third explanation I give for Nesterov method, is that this system now, you discretize it explicitly with the most naive way you can imagine, and you obtain Nesterov. You have not to go through indirect explanation, you see damping or link between procs. If you discretize this system, you obtain exactly yk here, or yk and exactly what, okay? And you have the same convergence rate, and Jordan, Millenbach, they obtain a related result, but in a less general situation. And just like to say a few words concerning recent research where we consider even more sophisticated model, where now we have 3 types of damping. You have the viscous damping, sorry, you have the Hessian damping, and you have the dry friction damping. Why dry friction? It's a subject of current research. It's just had been published in Cell 2020. It's very recent. Sharp, you see, there is a contrast between viscous damping. Viscous damping is associated with a fluid, like the air, the water, oil, you see. You have something which oscillates in a fluid, so it's going to stabilize smoothly. Dry friction, you have to imagine contact with a rough surface, you see. And if the force exerted of a system is below some threshold, then the system stops. And that's what happened with this kind of system, is that generically with respect to initial data, then you have finite convergence. Convergence within a finite time. But the point is that you don't end up with a minimizer critical point of f, but with an approximate minimizer of f, okay? Because the equilibrium, you see, when x dot is equal to 0, this is 0, 0, 0, 0, you have subdifferential of phi at 0 plus the gradient of f at x infinity contains 0. But when phi is smooth, which is smooth with viscous friction, this is 0, so you obtain a critical point. When phi is non-smooth, for example, phi is equal to r times the norm, this is a ball. This is the ball centered at the origin of radius r. So you obtain that the norm of this vector is less than r. So r is small, then you obtain an approximate critical point. And what's very interesting with this system is that it tolerates errors which are not converging to 0. They are just assumed to be bounded from above. This is enough in order to preserve the convergence property. And this may have some interesting application to stochastic problems.
Hedy, 2 minutes.
2 minutes. I just say a word concerning, in fact, all this theory can be extended to Monotone inclusion. I have not too much time. So recently with Laszlo, Cizlar Laszlo, say up 2020, we introduced this system, which is an extension of a previous system, where instead of taking the gradient, to take a maximal monotone operator, A. But you cannot just replace F by the maximal monotone operator, because in that case, it's ill-posed. The idea is to regularize the operator via its Yoshida approximation. And just the skill is to find the, and if you discretize, you end up with this kind of algorithm, which is a relaxed proximal algorithm. Here is the picture. You have extrapolation plus correction. And here you compute the resolvent, and you have some relaxation here between YK and the resolvent. Here is the algorithm, the structure of the algorithm. And we have obtained this kind of result for the algorithm. And the sensitive point is the tuning of lambda k. And we have fast convergence result and for general maximal and monotone operator. So I have just time to give some takeaway message. So we have been able to develop a dynamic perspective on accelerated optimization algorithm with viscous and Hessian-driven damping. Recall that we use both viscous and Hessian damping. Okay, you have to use both. The key is inertia. We have a unified analysis of convergence and integrability property. We have new probably accelerated algorithm without explicit Hessian construction. We use the Hessian, but we have not to compute it, since the Hessian only enters via its discretization, which may compute the difference of two consecutive gradient at two consecutive steps. The Hessian geometric damping neutralizes oscillation. So we get the best of two worlds. Convergence of iterates and trajectory, yes. Faster asymptotic convergence, yes. Application to inexact stochastic case, it's ongoing. And one of them, let's say, not drawback, but current research now. We have a tremendous field of application considering a general structured optimization problem and apply this technique to them. So I think that this is a subject for coming years and a very promising subject. I thank you. Thank you very much and for your attention, and I hope you had many questions.
Thank you very much for a great talk, very, very clear talk, very nice insight in the interplay between continuous time and discrete time approaches for optimization, in particular in respect to fast methods. So it is time for questions. Then yes, so.
Yes, can I have a question?
Yes, Jean-Liang.
Okay. The second order.
Where are you from? Can you tell us where you're from? Mr. Khan. Okay.
Hi.
So
yes.
Go ahead.
Okay. The second order system can be written as a Hamiltonian system you mentioned. So if we go that route, does those derivations, convergence theory can be carried out?
Sorry, concerning the first order equivalent system?
Yes, that's right.
Yes, yes. For the first order equivalent system, we do, in the continuous case, we did exactly the Lyapunov analysis and everything works well. The difficulty comes with the discretization. We have a lot of difficulties to transposing the result of a continuous case to the discrete case. Okay? The Hessian, when you have the Hessian, there are ways, at least two ways to deal with it. Just like we presented in this lecture, just saying that the Hessian term is the derivative of a gradient term, okay? And the other way is to write the equivalent first order system, okay? Just like I wrote at the, okay. That's the other way to attack this problem, okay? And this way is very interesting because it allows you directly to treat with a non-smooth function f, non-convex, non-smooth, you see, for steepest descent, you see, you have a rich theory concerning the non-smooth, non-convex setting. So at least when you take fixed coefficient here, you can use Kurdyka-Loyazevich theory and all these kind of things. And so you have a powerful tool. The difficulty is how to discretize this dynamic. It's very complicated, you see, how to discretize this and this and this, and at which point, you see, you have such many possibilities to discretize it that we must say that we have been lost. We obtain results, but we are not very exceptional results.
Yeah, another question. Here you see the function f is non-convex.
Yeah, it may be, yeah.
And if at convergence, which minimum you are going to converge to?
When it's not convex, the idea is to go through Kurdyka. We fixed with in the autonomous case, when you have fixed coefficient, the idea is to go through Kurdyka-Loyazevich theory. In fact, that's what Castera, Boltfeber, Powers did. The application to deep learning, they want to deal with non-convex, non-smooth problem. They use this equivalent formulation, you see, okay, in order to improve the steepest descent. You see, if you use the system, you improve the system descent since you introduce some geometrical tools into your dynamic. So it's better, it's a clever dynamic, okay? And you can show that this function, if f is semi-algebraic, then you have a semi-algebraic problem, you see, and you can apply the Kurdyka-Loyazevich theory, and okay, you apply the Kurdyka-Loyazevich theory not to the function f, but to some, let's say, energy-like function, which is a function of x and y. You can exhibit a function of x and y, which is semi-algebraic if f is semi-algebraic, and you can interpret this as not as a gradient method, as a quasi-gradient method with respect to this function which satisfies Kurdyka-Loyazevich theory. So you can end up with convergence property and rate of convergence if you have some, by using the rate of convergence of Kurdyka-Loyazevich. If you have some information about the geometry of f, you can devise, and I encourage you to read this nice paper, but it's very recent, you see, it's now 2019. And they use this system to attack non-convex, non-smooth problem because that's the natural setting for deep learning.
Okay, thank you.
Thank you. Matthias?
Yeah, thank you. I hope you can hear me. Thanks, Hedy, for this nice lecture. So I have a question about the stochastic case. If you would consider the stochastic case of your methods and then the corresponding algorithms, how would you actually start setting up the continuous time system? The second order continuous time system? What would be the corresponding equation here? Would you write first a coupled system first order equations? And if so, where is the noise coming in? How do you model this?
I say it's ongoing system, you see.
Okay.
In fact, with Jalal Fadili and some who are thinking about this problem, and I must say from my side, my first idea was to say, you see, think about the stochastic gradient method. The idea is each time you do some inertial gradient step, the idea is to introduce this correcting Hessian term, you see. This is a systematic philosophy, you see. You can consider all the class of first order algorithm when you have a block which is either a gradient block or proximal block to introduce this correcting term. My feeling is that this improves the algorithm. So I was interested with concerning stochastic inertial gradient method and introducing the Hessian. But finally, at this moment, I'm more interested with my concern was with this result. You see, I was very excited about this result because it's the first result I meet where you are not
I understand. No, I
assuming
understand the philosophy that you have here.
you are
of
not
course,
assuming that the
but-
error goes to zero, which I think is
Yeah.
very interesting for stochastic problem. And I think, for example, for this problem, you introduce some stochastic error, EK, and I'm sure that you can obtain almost sure convergence of the algorithm with this kind of situation, right?
At the algorithm, I would agree, but I would not see the equivalent continuous time system so immediately. Yeah,
No,
that
but
was my question essentially. So
see, I'm not an expert. I'm not an expert in the field, and
Yeah.
at this moment I'm learning about the stochastic differential equation and this kind. I think it's not easy. I think that's my opinion, but I think it's important. That was these were my motivation, and it's not a Gaussian error, but for numerical situation, if you have a stochastic errors which are bounded with some level of uncertainty, I think it may be interesting to consider this kind of model to take care of these stochastic errors. It's not Gaussian, but just you have some infinity bound on the error. At this moment, this is the situation that I have some intuition.
Okay, thank you.
Thank you. Other further questions? Then I have a question, Hedy. So in the beginning of the talk, in the first slide, so there was a coefficient b of t of the gradient, and then not much, was
you're right. But this is
later.
Yeah, this is another lecture. This is another lecture. In fact, you are right. In this kind of, for example, Jordan insists very much about this, and I'm also convinced this is some power of the dynamical approach. Since in the dynamical approach, there is a natural way to accelerate the trajectories, to accelerate the dynamic is just by time scaling, reparametrization of time, you see? That's something very important. And we have several papers which have been devoted to that, you see? But not to make the lecture too complicated. You see, I just presented a simplified model. But if you want at the end, maybe I have something for you at the end. It's they've just been published. It's EECT 2021, you see? It's a paper we've published with Spanian Riai and one of our students. We have been studying this system with general coefficient here. Okay, no restriction. General damping coefficient, general beta in front of the Hessian, and general B. And we have been analyzing this system. But the condition we have, which are very general, it takes one slide to write the coefficient, the condition. We have several conditions that are very complicated, but when they can simplify enormously in our situation. In our situation where here, we end up with this general scaling factor here. We are allowed to take, you see, this general scaling factor just as a constraint that D is non-increasing. Okay, we can develop the general theory with just the scaling factor with D non-increasing. And for example, the situation we consider just correspond to a limit condition to take D of T is 1 over T power T minus alpha minus 3. Okay, so it's decreasing, then you end up with 1 plus beta over T, which is exactly the coefficient we had. And if D of T is 1 over T power minus alpha 3, you end up with 1 over T squared. Okay, but you are allowed to take more general coefficient you see here. But if you do that, then it becomes very technical. And this is a very simple situation. You see, the general situation, there is one slide with 7 conditions, algebraic and differential condition, which gives you the and which condition and the coefficient you have convergence result.
But then then I have a difficult question, Hedy. So I notice and I agree that there is some benefit of having this B of t. But then if you discretize, so this leads to step sizes for the proximal operator, which increase, which approach plus infinity. Is this something good?
Yeah, you are right. You are right. That's why. In fact, that's what I'm. Let's say I'm not so excited about the rescaling method.
Okay.
They are very good for the continuous dynamic. Okay, but for optimization, ultimately, when you discretize, you apply some gradient lemma, and if you have a coefficient which goes to infinity, you are lost.
Yes.
It's not good. So I agree with you.
Okay.
Very interesting from physical, spherical point of view, but for our point of view, otherwise, still, there is an answer, okay? If you do gradient methods, I agree with you, it's not good, but you can do proximal method. Okay. If you do proximal method, it works. Which means that you can have very fast method with proximal method, but the price to pay is that the coefficient of a proximal goes to infinity.
Yes.
Okay, so you have degeneracy in the computation of a prox, but there's a price to pay. You see, you can accelerate the algorithm with B of t very large. You get a proximal step with very large coefficient. You can compute it, but it's ill-conditioned.
I agree. Thank you very much.
I have a question,
okay.
If there is enough time.
Yes.
So,
one more question. Yeah. Okay.
Okay, thanks. So you said, so in the beginning of the talk, you obtained a result in discrete time, which is based on a result on continuous time, and there are many years between the two results. Do you see what result I'm talking about?
So which slide do you consider? Which?
I don't know. I don't remember the number of the slide, but you said that you recently obtained a result in discrete time for an accelerated algorithm that you studied in continuous time many years before, like several years before.
It was the Hessian driven time. This was the 2002 result with Jerome, I guess.
In fact, what I say is that for the first order system, yes, for the first order system, we studied it in a continuous time and we succeeded in obtaining fast convergence result, but we failed to obtain corresponding discrete results.
Okay, but
it's
okay, that's one you obtained in 2020 with in discrete time, but maybe not with the Hessian dumping term. Or I'm sorry, I don't remember. I will watch the talk another time.
It was
it's in the first part of the talk.
No, it was in GDE. Sorry. Journal of Math Pure and Appliqué, 2002. Yes, we obtained this result. But with in this case, we obtained the result with a fixed damping. And in this case, we obtained the result with alpha over t. That's the big difference. Okay, so it took 15 years to go from, let's say, Polyak to Nesterov. 2002, we knew Polyak. We took a fixed damping coefficient. 2016, we knew via Suboid and Candace, we knew Nesterov when we introduced alpha over t. So we revisited this result in the perspective of Nesterov, but the computation is the same. You see, just algebraic computation, and in both cases, we're able to do asymptotic analysis and so on, but not the discrete analysis.
Okay.
With this system, we're a bit lost. We don't know how to discretize it. There is no natural way to discretize it.
So in general, when you do discrete time analysis, you use somehow the same Lyapunov function as in the continuous time. And yes or no? And also the Lyapunov function, it has a physical meaning, you said. and I would like to understand what kind of physical meaning it has. Like, is it a Hamiltonian or something like that?
The Lyapunov function? Yes, the Lyapunov function is a very natural interpretation. You see here. Sorry. Here is, you mean the Lyapunov function here?
For instance, yeah, for instance, this one, yes.
Yeah,
so,
this one.
Yeah. How can I understand this one from a physical point
here
of view?
It's written in a condensed form. You see here it's hidden by is the norm of square. You see, when you develop the square of the norm here, you have the square of the velocity. So it's the kinetic energy. You have a potential energy. So you have a global energy plus the square of the distance from x to x star. So it's a natural combination between the two quantities which have a limit, which is the global energy, which is decreasing along the trajectory, and the distance to equilibria, which have a limit. So you mix them and with ad hoc coefficient. If you don't know a priori the coefficient, we take them as unknown, do the computation, and you just identify them in order to get the right sign, you see, in order to have a quantity less or equal to 0. Okay, but this is now something which is more or less natural Lyapunov functions.
Okay, and if I may just
is okay when there is no variation, beta is equal to 0. This is exactly the global energy plus the anchor function. But here, when beta, you have to modify x dot by considering x dot plus beta gradient of fx.
Okay. Just, yes, a very last question. So regarding monotone operators, monotone inclusions, so what is the current state? So you have acceleration for continuous time dynamics. Do you have the discrete time? Because it went so fast.
Yeah. And not too much time to develop it, but with Laszlo, this is the discrete time.
Okay, discrete time. So do you have
quite technical and not time enough in order to detail the result? But you see, if you take the right tuning of the Yoshida regression parameter, what is essential, you see, A is a general maximal monotone operator. If you want to develop inertial method for maximal monotone, general maximal monotone operator, it doesn't work. Since you have rotation, you see, and because of the inertia, the trajectory are even not bounded. So you have to regularize the operator in order to reduce the operator to a coercive operator, right? That's the right. Okay. That's the right. I'm sorry, my wife is back from. And you have to reduce. You have to reduce to the co-coercive case by replacing A by Yoshida approximate. Okay, that's the idea. And the scientific point is the right tuning of the Yoshida approximate parameter. If you take the right tuning for the lambda approximate, then you have a co-coercive operator. It's adapted to the Nesterov acceleration. And then you have these are very good rates of convergence, you see. This replaces the convergence of a velocity or convergence equivalent of a convergence of a gradient. You have fast convergence of this quantity, convergence of the trajectories, and so on.
So do you have
since we only develop it for the moment in the case of a general maximal monotone operator. Then you have to consider structured monotone inclusion, and there is a lot of things to do. You can consider you can consider ADMM and all this method. And the idea is to apply this kind of techniques, and you end up with what we called proximal regularized inertial Newton algorithm for monotone operators. Okay. It's proximal regularized inertial. This is the structure of the algorithm. And when you have a structured problem, the idea is to use this topic to each block, you see? since you see the damping has been adapted to the geometry of a problem. When you have a structured problem, the idea is to adapt the damping to the block you consider. For different blocks, you are going to consider different type of damping correcting terms, right? But this is something to develop, and I think there are many papers to write, and not to speak about Tikhonov regularization also in this setting, which will be very interesting and so on. And I have ideas, but I'm not able to explain all of this.
Okay, thank you. So then
Thanks.
I propose to stop here. Thank you very much. Thank you for a nice talk, Hedy. Thank you for the discussion, for the questions. I just want to announce that we will post the video and the slides on the website of the seminar. And that, of course, I said at the beginning that this year is the last season of our seminar, like in the form of a negative message. But the positive message behind is that we will have also in the third season very great speakers who already agreed to talk in the framework of our seminar. So I'm looking forward to meeting you in our seminar in the next weeks, every Monday. Thank you, Hedy, for a nice talk. Thank you for a nice opening of the third season. Wish you all the best and have a nice week. Thank you and bye-bye.
Thanks a lot. Thanks a lot.